All right, so it turns out there are some exceptions to the general filling principle, and I'm going to ask you to know 4 of them. So the first one is chromium. So you could describe chromium as argon with 6 more electrons to it. And you might think that those 6 electrons, you would just go, 1, 2, 3, 4, 5, 6. But it turns out that it actually takes a small amount of energy to flip the spin of an electron and to actually put it into an orbital or a state that already has an electron. And in particular, the energy difference between an S subshell and the D subshell right above it is very small. And in many cases, it can actually be smaller than that, the energy that it needs to flip the spin. So rather than pair up, this we just start putting electrons in these states. And so in the case of chromium, excuse me, that energy difference is more, the spin flip energy difference is more than the difference between the 3D and the 4s subshells. So experimentally, its electron configuration is found to be an argon core 4s2 3d5. And the element right below chromium, molybdenum, also does this. So those are the 2 of the 4 exceptions that you need to know. So molybdenum too. All right. And not 4s2 3d4. Another way of saying this are that half-filled subshells are also particularly stable. So note that both of these subshells are exactly half-filled. The other exception, so it turns out that completely filled subshells, especially Ds, are also a little favored. So copper, so just going down to the end, or going down to that row, about the middle of that row. Copper is argon plus 11 electrons. And so you might think that you've got just 2 4s electrons and then 9 electrons in this 9 3d type electrons, but that is not the case. The relative energies of these can actually jump around. And again, and in some cases, depending on how many electrons of each type you've got, the 4s might actually be higher in energy than the 3d. It's pretty complicated. But experimentally, you find that the electron configuration of copper is actually an argon core 4s1 and then 3d10. So that's one of them, and not 4s2 3d9 like you would expect otherwise. And the element under copper in the periodic table, which is silver, Ag, also has that exception. All right. So the last thing we need to talk about with electron configurations are how to deal with ions, because ions are everywhere. So anions are actually pretty simple. You start with the electron configuration of an atom, a neutral atom of that element, and just add the appropriate number of electrons, whether it's 1, 2, 3, and so on. So for example, fluoride. So fluoride has 10 electrons. It is fluorine with one other one, so 9 plus 1, 10. The electron configuration of a neutral fluorine atom is 1s2, 2s2, 2p5, and you just add one more. So now you get 1s2, 2s2, 2p6. Positive ions, cations, little trickier. So basically, you start with the configuration of an atom, a neutral atom of the element, and take away the appropriate number of electrons. Question is, which ones do you take out? And the answer is, it depends. All right, so main group metals, cations, are pretty simple. Just take away the electrons with the highest N, the p types if they're present, then the s. So this is sort of like a last in, first out rule. So for example, sodium. A sodium ion has 10 electrons, one less than a neutral sodium atom. The configuration of a neutral sodium atom is 1s2, 2s2, 2p6, 3s1. You need to take one out. This is the one that goes. And so the configuration of a sodium ion is just 1s2, 2s2, 2p6, neon. All right, transition metals, the ones in the middle, that block a 10 in the middle that is, always difficult. They're a little different. The rule there is you take electrons out with the highest value of N, P, then S, and then if you need to, D electrons in the next shell down. Now this is not the way that you fill them in. So for example, iron. Neutral iron atoms have a configuration, they have an argon core and then 4s2, 3d6. So the last 6 electrons that you threw into that were these 3d electrons. But the rule is that, so iron is quite happy being +3 ion, a +3 ion. So we need to take 3 electrons away from this configuration. But nature tells us that you actually take the 4s electrons out first. And then one of these d-type electrons if you need to. So the electron configuration of iron is argon 3d5 and not argon 4s2 3d3 that you would otherwise think it would be. All right. So do plenty of examples of these. And in case you're wondering what the song tie-in was, Hund's rule that tells you that they don't pair up until they need to. So Hund is actually the German word for dog. The artist that does this song is Three Dog Night, or in German it would be Die Hund Nacht. All right, see you at Zoom.